and we are, I think, at Roman numeral number 4. And tonight we are looking at neutralization reactions. So typically when we mix an acid and a base, we always get the same thing, and these are neutralization reactions. And we might just say an acid plus a base yields water and a salt. Alright, and really what we're looking at tonight is the pH, or what is the pH going to be? Alright, and there's several different things that can happen, so our pHs can be several different things. And this will really kind of take us back to the lab we did beginning of January, where we had the different cations and anions, and seeing whether they're basic or not, basic or acidic. So, several scenarios can play out. Our first one we're going to look at is a strong acid with a strong base. A strong acid plus strong base, and these will always yield water, and we might just say a neutral salt. So a salt that does not change the pH, but a neutral salt. Okay, kind of a couple things we need to define is what things make up strong acids, and we've seen this list lots of times, but HCl, HBr, HI, whoops, we got H2SO4, got HNO3, and since we're doing acid-base chapter, we're going to add HClO4. Okay, and then strong bases are going to be things with alkali metals, or really alkali and alkaline earth, alkaline and alkali earth. So groups 1 and 2, with the exception of beryllium. Alright, so again, you might just write that group 1 and 2 instead of alkali and alkaline earth metals. Okay, so we might just have an example. We're going to do an example of all these. Probably our easiest example is hydrochloric acid plus sodium hydroxide, and these things give us water, and they give us really sodium ions floating around and chloride ions floating around. Or we might just write that sodium chloride. But again, this is the anion of a strong base, and this is a group 1 metal. Okay? And really with this, if we have equal molar amounts, so if we had 2 molar HCl and 2 molar NaOH, our pH should be 7. Alright? There's not a limiting reactant, everything's going to get used up, and we're making water and stuff that does not react with, and cations and anions that do not react with water. So our next scenario is going to be a strong acid plus a weak base. Alright, and in this scenario we get water still, and we get acidic salts. And we might just say our pH is going to be less than 7. So pH is less than 7. Alright, because we have salts that produce acidic solutions. So, let's see. I think we're just going to skip to an example. So, we'll just use HCl again as our strong acid, and we're going to react it with ammonia. Alright, and in this scenario, we are going to get ammonium ion, and we are also going to get chloride ion. Okay? So we know the chlorine does not contribute to the pH changing, because the chloride itself is neutral, because it's the anion of a strong base. So we really have NH floating around, and because these are already in solution, we really end up getting NH4, or ammonium, in the presence of water, and we know that hydrolysis occurs here, so that we get ammonia back, and we get hydronium ion. Okay? Something that kind of looks like that. Okay? So, in this case, because we are producing H3O+, our pH is less than 7. Okay? Our next is going to be a weak acid with a strong base. And in this case, we're going to get water, and we're going to get a basic salt. And we get pHs that are greater than 7. What are some other weak bases we can have? A lot of these are going to be things that have, we're kind of going back up to B, but just some more examples. We might have small cations. So if you remember back to our aluminum ion or zinc ion, we could include the beryllium ion right here, since we didn't have it above. It's not really a strong base, but a weak base. Iron is another common one, Fe3+, and maybe chromium 2+. Okay? So again, let's go back to where we were before I got sidetracked. So weak acids plus strong bases. And just some examples of weak acids. And we'll put them in green over here to the side, just like we did the last ones. So maybe cyanide or hydrocyanic acid. Some other weak bases, we might do just nitrite, which makes nitrous acid. Fluoride, hydrofluoric acid's weak. And another common one would be acetic acid, so acetate ion. Alright. So from that, again, we'll throw just an example up here. And our example this time is going to be HF, so hydrofluoric acid, plus sodium hydroxide. It's a strong base this time. And we're going to get water. And because sodiums are always soluble, we're going to have some NAs floating around, and we're going to have some F minuses floating around. So obviously our Na is the cation of a strong base, so it does not contribute to pH at all. But F does. Okay? So really what we have floating around is some F minus, and it's floating in the presence of water. Alright, and that is going to produce HF. Alright, so we're going to get our weak acid back. And in that process, we're going to make some extra hydroxide. Alright, so because we have hydroxide ions floating around, our pH is greater than 7. Okay, which means we have a basic solution. And then our last scenario is that we could have a weak acid and a weak base. Alright, and in this case we are going to get water. And in addition to that, we're going to have some acidic cations and basic anions. And really we're going to have to look at the strength of our acidic cations and the strength of our basic anions to find out what the pH is going to be. But the pH could range between being slightly basic or slightly acidic. So if we kind of use just our anions from above that were our weak examples, so HF plus an H3, we get ammonium and we get fluoride ion. Alright, so a couple things then can happen. We can have ammonium ions floating around, and they're going to be in the presence of water, and what we're going to get is ammonia back, and in that process we get hydronium. But then at the same time we have fluoride ions floating around in the presence of water, and we know hydrolysis occurs, and we get HF back, and we get hydroxide ions. Okay, so this produces something acidic, and this is producing something basic. Alright, so when this occurs, we need to compare then our Ka and Kb values. So compare Ka and Kb values for these weak acids and bases. Alright, and again, these are found on page 557 of your book for the acidic, and page 564 in your book for the basic. But if we look at NH4, because it is going to show up under the bases, its Kb value, so NH4, has a Kb of 1.8 times 10 to the negative fifth. Where if we look at 557, we're going to find F minus, alright, and it has, because it is a, if we put H here, it's an acid, it has a Ka value of 7.1 times 10 to the negative fourth. So we really just look at these and which one is the larger value. And the larger value happens to be Ka. So this reaction, I'm just going to circle it in red, this reaction is going to be slightly acidic, or our pH is going to be less than 7 because our Ka is larger than our Kb.